In this video we will take a look at fractional number conversions to different radixes R. We will explore initially decimal to binary fractional number conversion just using tables, and then we will develop systematic decimal to radix R number conversion of fractional numbers of any lengths. And we will also discuss precision and rounding issues that arise in connection with fractional numbers. In general, we look at radix R number representations of the following form: capital N sub R, which we have been using to denote such numbers, is equal to n sub k sub 2 minus 1, n sub k sub 2 minus 2, all the way down to n sub 0. And then comes the radix point, and then we have n sub minus 1, n sub minus 2, and m sub minus k minus 1. And what this means is that we have here k sub 2, capital K sub 2 digits to the left of the radix point, and we have capital K sub 1 digits to the right of the radix point. Okay, and we call the left side the integer part and the right side the fractional part. In general, the conversion from decimal to radix R representation takes on different forms depending on whether we work on the integer part or the rational part, the fractional part. So we denote the integer part I sub R and the fractional part capital F sub R, and we are only going to be concerned here with the fractional part capital F sub R. Okay, so we will start from this formula here. Capital F sub R is equal to k equal to 1 up to capital K sub 1 n sub minus k times r to the minus k for k sub 1 radix R representation of this fractional number, or this fractional part of the number f sub R. So a simple and straightforward case to convert from decimal to binary is if we just go ahead and we just take a look at 0.5 in decimal, which in binary is going to be 0.1. In decimal, 0.25, which is 1/4, is going to be 0.001, 2 to the minus 2. And then 0.125 1/8 is going to be equal to 2 to the minus 3. And that is 0.001 in binary representation. And we can continue this way quite easily. And of course we could add some of those things together. In fact, that's what we are doing if you are looking now at the table of binary or decimal to binary conversion. Okay, so we start out with 0.000, which of course in binary, which is of course 0.0 in decimal, then 0.001, that's 1/8, so that's 0.125 in decimal. 0.010 in binary is 0.25 in decimal. 0.011 is 1/8 plus 1/4, so that's 3/8, that's 0.375, and so on. And if that resolution is not good enough, we can start looking at the numbers in between those which we are just showing now in the table, and we can go to a 4-bit representation of the fractional part, and we get, for example, 0.0001, which is 1/16, is equal to 0.0625, and then if you take 2/16, that's 1/8, 0.125, 3/16, 0.1875, and in binary 0.0011, and so forth. And we could continue this table. But one of the big disadvantages here is that if we were, for example, to try to compute the decimal number 0.1 to 4 decimal digits and represent that in radix r, or binary representation in this case, radix r equal to 2, we would have to do quite a few additional entries in the table by extending the number of bits, and it would become very unpractical. So we need a more systematic approach for that whole thing. And what we are going to do is we're going to take f sub r, which is k equal to 1 up to capital K sub 1 n sub minus k times r to the minus k. So this is f sub r here. And we're going to multiply this by r, so we compute r times f sub r. Okay, so that gives us k equal to 1 up to capital K sub 1 n sub minus k times r to the 1 minus k. And we are now going to pull out the first member of the summation, so we're going to write this as being k equal to 2 up to capital K sub 1 n sub minus k times r to the 1 minus k plus n sub 1. So this is the first member of that summation. Then we do a change of variable and let little k become little k plus 1. And so effectively we are shifting down that summation that goes from k equal to 2 up to capital K sub 1 to going from k equal to 1 up to capital K sub 1 minus 1. And then times n sub minus k minus 1 times r to the minus k plus n sub minus 1. And so now what we observe here is that the n sub minus 1 over here, this is going to be an integer. It could be 0, but it could be 1 when it's binary, or it could be 1, 2, 3, 4, 5, and 6, and 7 when it's octal and so forth. Whereas the part here to the left, because it starts at k equal to 1 and gets multiplied by r to the minus k, this is always going to be less than any of the integers here. So this is always going to be a fractional part. And so what we effectively did, of course, by multiplying r times f sub r, is we shifted the whole thing to the left. So we went from our original version. Let's draw this in a different color here. Okay, so we went from n sub minus 1, n sub minus 2. Oops, that should be a minus in there. Up to n sub minus k1, and the radix point here doesn't want to make radix points. Okay, the radix point there, let's make this a little bit bigger here. So this is the radix point. So we went from that representation to this one over here, where we shifted the whole number to the left by this multiplication by r. And so now we have to the left of the new radix point n sub minus 1, and to the right we have the remaining fractional part, which constitutes, or which consists of n sub minus 2, n sub minus 3 up to n sub minus k1. And of course we can repeat that now. We can take this k equal to 1 up to capital K sub 1 minus 1, n minus k minus 1 times r to the minus k, which is the new fractional part, multiply this by r, and thereby shifting everything to the left again by r. We go through the derivation here. We take the first member of the summation out, which is n sub minus 2, and because we have n sub minus k minus 1 here, and at k equal to 1, that's n sub minus 2. And then we go from k equal to 2 up to capital K sub 1 minus 1 of n sub minus k minus 1 times r to the 1 minus k. We do our change of variable again. Little k becomes little k plus 1. So now we have shifted again the range of the summation down by 1, so we go now from little k equal to 1 up to capital K sub 1 minus 2 of n sub minus k minus 2 times r to the minus k plus n sub minus 2. And so we are again at the point where we have here an integer part and here the remaining fractional part. And so we have now effectively the representation n sub minus 2 and then radix point and then n sub minus 3, n sub minus 4 up to n sub minus capital K sub 1. And we can see that we can use that procedure now recursively, and we're going to shift once more to the left. We get n sub minus 3 out and so forth. Okay, now in general, that remaining fractional part after m such operations, after m recursions, will be k equal to 1 up to capital K sub 1 minus m of n sub minus k minus m times r to the minus k. But this will not be equal to 0 in general. Okay, so we need to have some precision criterion to know when we should stop with the conversion. We find that if we want to have a precision of p decimal digits in radix r representation, then we need approximately little m equal to logarithm to the base r of 10 to the p and the next highest integer, which is equal to logarithm of 10 to the p over logarithm of r, where this can be any logarithm, but the numerator and denominator logarithm have to be the same. Or we can express it like this, as p divided by logarithm to the base 10 of r, if we compute this in the base 10 logarithm. And again, this graphical representation here means that it's the next highest integer that we're going to take. It's the ceiling function. Okay, so this is the number of digits, the number of radix r digits that are needed for the conversion. Okay, so let's take a look at an example. And in fact, we're going to take a look at this initially just as a live derivation. So we want to represent f10 equal to 0.1, so decimal 0.1 in binary to a precision of p equal to 4 decimal digits. We find that we need m equal to 4 over logarithm to the base 10 of 2. So that turns out to be 13.29, and then we take the next highest integer, so that gives us 14 bits for this binary representation of 0.1. So we're going to start out here with, let's do this in a different color. We're going to start out with 0.1. That's the number, the decimal number that we want to convert to binary. We multiply by 0.2. We multiply by 2 to obtain 0.2. Okay, so times 2 gives us 0.2. Okay, so that's now the shifted representation, and we can see that we have a 0 in the integer part and the 0.2 in the fractional part, so we do not change anything in the integer part, but we note that n sub minus 1 is going to be equal to 0. Okay, and then we take that 0.2 and we multiply it by 2 again to obtain 0.4. So the integer part is still 0, so that means n minus 2 is equal to 0. And we continue with the fractional part, 0.4. Okay, so we take 0.4 times 2. That gives us 0.8. Our integer part is still 0, so n minus 3 is equal to 0. And we take 0.8. Let's rewrite that here. So we take 0.8 times 2. That gives us 1.6. So now we have an integer part which will go into n sub minus 4 equal to 1. And we have a fractional part, 0.6, that we use to continue our computation. So now we have 0.6 times 2, that's equal to 1.2. So that means n sub minus 5 is going to be equal to 1. And 0.2 is the fractional part with which we continue. 0.2 times 2 gives us 0.4. Okay, so n minus 6 is going to be equal to 1. Then we have 0.4 times 2. Oops, that should be a 0.4 here. That is equal to 0.8. Okay, and so n minus 7 is going to be 0. And then we have 0.8 times 2, that gives us 1.6. And of course, we see that this becomes periodic here. So we have n minus 8 equal to 1. And 0.6, the fractional part that we continue with, times 2. That gives us 1.2. Gives n minus 9 equal to 1. And so forth. Okay, so for one thing, we see the periodicity here. So we have 0.4 is the first one that gets repeated. So we have a period here. And then, actually, no, it's one less than that. Okay, so it goes from here to here. It's a period of 4. And then we start again with 0.4, 0.8, 1.6, 1.2. So this is the next period. And it continues this way. And in general, this will happen when we have a fraction that cannot be expressed exactly in radix r. They will become periodic. Okay, so now we can look at what we have been writing before here. We get this 000 for the first 3 digits after the radix point, and then 1 1, and then 0 0 1 1 0 0 1 1 0, and then we actually did continue beyond the 14th digit to see what the next one is. And the reason why we do that is because if that would have been a 1, then we would have to do rounding of the last digit here. But this is a 0, so we can just cut off here at the green line. And so we find that the binary representation of 0.1 to 4 decimal digits is going to look like this. So it's 0.0001100110011. The last 0, of course, is not necessary to write, but we just show here that we went to 14 digits. We can check that this is indeed the right decimal value. So we compute the value of f2 as 2 to the minus 4 for the first one here, 2 to the minus 5, then 2 zeros, and then 2 to the minus 8, 2 to the minus 9. And the last 2 is 2 to the minus 12 and 2 to the minus 13. And if we compute that, we find this is 0.099975585 and some more digits here. Okay, and if we round that to 4 digits, okay, the 7 here is greater or equal to 0.5, so we have to add 1 to the last, to the 4th digit, and so we get 0.1000 as we wanted it to have. One of the things that we notice here is that in the decimal number system we are very much used to take things like 0.1 or 0.2, or for example add 0.1 plus 0.1 plus 0.1 and then get 0.3. If this is done on a binary computer with a relatively small resolution or precision, then we will expect after a couple of such additions of the approximation to 0.1 that we might actually get a deviation. Okay, so now let's go and try the same thing for a ternary number. So we want to take again f10 equal to 0.1, the decimal 0.1, and now represent it in ternary. We compute how many ternary digits that we need if the precision of 4 decimal digits is required. So we have 4 divided by the log 10 of 3. That gives us 8.38. We take the next highest integer, that's 9. So we're going to need 9 ternary digits for this. Okay, so we start out with the 0.1 that we want to convert. We multiply by 3, and we use now a more abbreviated notation here. So that gives us 0.3. The integer part is 0, so n minus 1 is 0. We multiply this by 3, that gives us 0.9. The integer part is still 0, so we get n minus 2 is equal to 0. And then 3 times 9 is 2.7. So the 2 goes over here, that's the integer part, and becomes n minus 3. And the 0.7 stays over here, gets multiplied by 3, gives us 2.1. So the integer part of that goes over and becomes n minus 4. And the 0.1 continues, times 3 is 0.3. And then again, and so that there is an integer part of 0, which is n minus 5, and then we multiply by 3 again, and so forth. And again, we see that this whole thing is periodic here. So we have 0.1, 0.3, 0.9, 0.7. So that's this thing here, and then 0.1, 0.3, 0.9, 0.7, and so forth. And we find that the ternary representation of 0.1 in decimal is equal to 0.00220022, and then there is a 0 at the end. Again, we went here one more than 9 ternary digits in order to see whether we need to do rounding or not. And it's a 0, so we don't need to do rounding. And so this is our representation. We check again. This is 3 to the minus 1, 3 to the minus 2. The first non-zero one is 3 to the minus 3. So we have 2 times 3 to the minus 3 plus 2 times 3 to the minus 4. Then 2 zeros, so the next one is 2 times 3 to the minus 7 plus 2 times 3 to the minus 8. If we compute that, we find it's 0.09999847 and more digits. And we truncate it, or actually round it, to 4 decimal digits. So because we have an 8 as the first digit after the fourth, we round the 0.999 up to 0.100, and we get 0.100, the decimal value, rounded to 4 decimals as we were desiring. Okay, let's do this for octal. So again, we convert decimal 0.1 to radix r equal to 8. We need 4 over the logarithm to the base 10 of 8, which happens to be 4.43, or the next highest integer, 5 octal digits. And we do the same thing as we did before. We take the 0.1 that we start from, multiply by 8. That gives us 0.8. So the integer part is 0. So n sub minus 1 is 0. And we continue with the 0.8 times 8. That's 6.4. So the integer part, 6, goes over here. That becomes n minus 2. And the fractional part, 0.4, continues, being multiplied by 8. That gives us 3.2. So n sub minus 3 becomes 3, and the 0.2 continues times 8, and we get 1.6. So there's the one over here. The 0.6 that stays back here gets multiplied by 8, and that is equal to 4.8. So the 4 goes over here, and the 0.8 stays over here, and then we do one more. We need only 5 octal digits, but we do one more to see if we need to do rounding. So we have 8 times 0.8, so that gives us 6.4. So that gives us the 6 over here and the 0.4 for the fractional part. And in this, first of all, we see that this is again going to be periodic. We started out here with having a 0.8. The first one is not necessarily included in the periodicity, but some of the later ones are. So we have 0.8, 0.4, 0.2, 0.6, and then it starts with 0.8 again. So this would be periodic again if you would continue. So this time now we have as the last digit beyond of the octal precision that we need, a number which is larger than the radix divided by 2, or larger or equal to than the radix divided by 2, which would be 4 here. So we have to round up to get the best precision that we can get. So instead of 0.06314, we're going to take 0.06315, the rounding up here, as our octal representation of 0.1. Okay, so that's what we have over here, 0.06315. And we compute whether that is actually correct. We compute the decimal value. We have 6 times 8 to the minus 2 for the first non-zero digit here, 3 times 8 to the minus 3, 1 times 8 to the minus 4, and 5 times 8 to the minus 5. That gives us 0.1 and then 40,61035. And if we round that to 4 decimals, we just simply have to cut off here after 4 decimal positions, and we get 0.1000 as we wanted to have. And finally, we're going to do this also for hexadecimal. Let's see, here it is. So again, we use the decimal number 0.1, and we want to express it now in hexadecimal. 4 divided by the logarithm of 10 to the base 10 of 16 is 3.32, and so we're going to need the next highest integer 4 hexadecimal digits. And we compute here in the usual way again, 0.1 times 16, that gives us 1.6. So the integer part 1 becomes n minus 1. The 0.6 continues. 0.6 times 16, that happens to be 9.6. So the 9 here goes to n minus 2, and the 0.6 continues. And here, in fact, we see that the periodicity is equal to 1. So we get, for the hexadecimal representation, that this is 0.199999, and because the last digit beyond the precision that we are using is going to be a 9, which is larger, greater or equal to 8, r over 2. We round up, so we actually round this now to 0.199a. So the 9 gets rounded up to 10. But in hexadecimal, of course, we write this as an A. Okay, we check again. 1 times 10 to the 16 to the minus 1 plus 9 times 16 to the minus 2 plus 9 times 16 to the minus 3 plus 10 times 16 to the minus 4. That gives us 0.1 and then 40,61035. So we can cut off here at the 4 decimal digits. And we do indeed get the 0.1000 that we wanted to have with that hexadecimal representation. Now, one thing we note here is that we can actually derive all binary related or power of 2 related representations from this representation. So we take F16, which we just found is 0.199a, and we can convert this to binary by representing each of the hexadecimal digits with the binary representation. So 1 becomes 0001, 9 is 1001, and another 1001, and A is 1010. And so we just can write this out here. F2 is equal to 0.00110011001101, as we have found before for the binary representation. And this time it was, for this particular case, it was much easier to compute because we had several things in our favor here. We had, first of all, we only had to compute 4 hexadecimal digits. And then it turned out that the period for computing those was only 1. So we had to compute a 1 and then a 9, and then from there on it was all 9s. So it is shorter and happened to have a shorter period. That's not always going to be the case, but it's certainly going to be shorter than the binary representation. And so we have less computation to do, even though the computation is a little more complicated because we have to now multiply things by 16. But at any rate, we get the binary representation here of 0.1. And then we can go and we can group this in groups of 3 to the right, starting on the right of the radix point. We take groups of 3 bits, so that gives us a 0, and then 1, 1, 0 gives us a 6, 0, 1, 1 gives us a 3, 0, 0, 1 gives a 1, 1, 0, 1 gives a 5, and so now we have the octal representation. Okay, so the easiest in this case is actually to compute the hexadecimal representation first, and then get the binary from that, and from the binary get the octal.